These are the notes for section 7.1. In this chapter, I'm trying to help you figure out how you can read a math book and figure out what the important parts are and what you should write in your notes. So for the notes, I have some copies of what it says in your textbook, and we're going to read that together, and then we'll figure out what we should write down in our notes. So it says a statement of equality between two expressions that is true for all values of the variable or variables for which the expression are defined is called an identity. For example, x squared minus y squared equals x minus y times x plus y is an algebraic identity. And it's an identity because it's always true. No matter what x and y are, x squared minus y squared always equals x minus y times x plus y. An identity involving a trigonometric expression or expressions is called a trigonometric identity. The important things we should write down in our notes are the parts that are highlighted. So let's write down a definition for identity. An identity is an equation that is true for all values. No matter what we put in for x and y, it's always going to be true. If you can show that a specific value of a variable in an equation makes the equation false, then you have produced a counterexample. It only takes one counterexample to prove that an equation is not an identity. And that makes sense because an identity has to be true all the time. So if I find even one time that it's not true, it's not an identity. For our notes, we should write down what a counterexample is. A counterexample is an example that shows the equation is false. And if we're trying to show something's not an identity, we only need one. There might be lots of right answers, but we only need one. So let's try that in an example. Prove that sine x cosine x equals tangent x is not a trig identity by producing a counterexample. So sine of x times cosine of x does not always equal tangent of x. And we need to find some specific number for x and show that the sine of that number times the cosine of that number does not equal the tangent of that number. That'll be a counterexample. As we're picking values for x, we want to pick values that are easy. And easy values would be like anything on my unit circle. So 0, 90, 180, 270, or any of the values from our special triangles, 30, 60, or 45. Those are all going to be values where it's really easy to find the sine, cosine, and tangent. We can do them using special triangles. So those are the values we want to look at when we're trying to find a counterexample. We can start by trying 0 for x. That seems like the easiest one to try. And I think in this case it's not going to work out, but we'll try it and see how it goes. If we put 0 in for x, then we have the sine of 0 times the cosine of 0 equals the tangent of 0. Using my unit circle, the sine of 0 is 0. The cosine of 0 is 1. And the tangent is sine over cosine. So 0 over 1 is just 0. Now, unfortunately, that's true, so we did not just find a counterexample. That's one of the few times when this happens to be true. So this did not work for us. We need to pick another value for x and see if that gives us a counterexample. I'll let you know now, if you pick 90, 180, or 270, for this particular one, it's not going to yield a counterexample. So we're going to have to either pick 30 or 60 or 45, and I think any of those three will work. I'm going to pick 45 and use my 45, 45, 90 triangle and plug those values in and see if we get something that's true or something that's false. Sine of 45 is square root of 2 over 2. So is the cosine of 45. And the tangent of 45 is 1. But that equation isn't true. Square root of 2 times square root of 2 would be square root of 4 over 4. Square root of 4 is 2. So in this equation, we actually have 1/2 on the left equals 1 on the right. That's not true. So x equals 45 does give us a counterexample. A counterexample is an example that shows that it does not work all the time. It might work some of the time, like in this case it does work when x is 0, but it doesn't work all of the time. It doesn't work when x is 45. So that's a counterexample, and that's what we were looking for. Although producing a counterexample can show that an equation is not an identity, proving that an equation is an identity generally takes more work. That's where we're going to have to do the steps. And we're going to have to use things that we already know are true, like all of these reciprocal identities and the quotient identities. Take a minute and pause the video and make sure that you have all of these identities written down in your notes. These are things that are true, that we already know, that we can use when we're trying to prove things are identities. Another thing we can use to prove that things are identities are the Pythagorean identities. So take a minute and make this picture in your notes, and pause the video if you need to. With that circle picture, we're going to get our Pythagorean identities, because on a unit circle, all the values of any point on the circle are cosine of the angle, comma, sine of the angle. So in that triangle, the Pythagorean theorem would say leg squared plus leg squared equals hypotenuse squared, or x squared plus y squared equals 1 squared. But since x squared and y squared are actually cosine squared and sine squared, we get the Pythagorean identity, sine squared plus cosine squared equals 1. You can take that identity and get another identity that's true by taking what we just figured out and dividing everything by cosine squared. When you do that, you get a second Pythagorean identity, tangent squared plus 1 equals secant squared. Here's something that math textbooks do a lot. It says, likewise, the identity 1 plus cotangent squared equals cosecant squared can be derived by dividing each side by sine squared. Math textbooks a lot of times leave out repetition, and they write things down that make sense to the person who wrote the book, but it might not make sense to you. It's a good idea at this point to stop and see if it makes sense to us. So they're saying you couldn't get this identity by dividing each side of the equation sine squared plus cosine squared equals 1 by sine squared. Let's confirm that that's true. If we start with sine squared plus cosine squared equals 1 and divide everything by sine squared, sine divided by sine is 1. Cosine divided by sine is cotangent, so cotangent squared. And 1 divided by sine is cosecant squared. And that's what they said we were going to get. So if you're ever in a situation where you're trying to read a math textbook, you really need to read slowly and carefully and stop and write some stuff down every once in a while to make sure it makes sense to you. Now we've figured out the 3 Pythagorean identities. These are identities that you need to have memorized for your Chapter 7 test. And as long as you can remember the first one, sine squared plus cosine squared equals 1, you can get the other 2 by just dividing everything by sine squared or dividing everything by cosine squared. So you don't really need to memorize all 3. You can memorize 1 and then just be able to use that 1 to get the other 2. Let's use the identities to do some things. Use the given information to find the trig value. If secant of theta equals 3 over 2, find the cosine of theta. There are a couple different ways to do this. One way is to see what's the relationship between secant and cosine. Secant and cosine are reciprocals of each other. So if the secant is 3 over 2, the cosine would have to be 2 over 3. Another way to do that, like we've done before, is to use the first picture to draw a triangle. I have an angle, and the secant of that angle is 3 over 2. Then use your picture to find the cosine. Cosine of the angle would be adjacent over hypotenuse, or 2 over 3. The triangle method still works, but there is a way to do it using identities also. Let's try part B. If the cosecant of theta equals 4 over 3, find the tangent of theta. There isn't a quick and easy identity that relates cosecant and tangent, but there is a Pythagorean identity that relates cosecant and cotangent, one of the Pythagorean identities. And we want to use the one that says cosecant squared plus 1, or sorry, cosecant squared equals 1 plus cotangent squared. Cosecant is 4/3, so cosecant squared is 4/3 squared. And that equals 1 plus the cotangent squared. Squaring the fraction gives us 16 over 9 equals 1 plus cotangent squared. Subtract 1 from both sides, and 1 is like 9/9 to get a common denominator. So 7/9 equals cotangent squared. Take the square root of both sides, and don't forget your plus or minus. To get that, the square root of 7 over the square root of 9 plus or minus equals the cotangent of theta. But we actually wanted the tangent, so the tangent is going to be the reciprocal of that. Flip it upside down. Square root of 9 is actually 3 over the square root of 7, and keep the plus or minus out front. For the final answer, just get rid of the square root that's in the denominator by multiplying the top and the bottom by the square root of 7. To get your final answer that the tangent equals plus or minus 3 square root 7 over 7. We could have gotten that exact same answer by drawing a triangle. If we would have drawn a triangle that has a cosecant of 4 over 3, that would mean the hypotenuse over the opposite is 4 over 3. And then we're looking for the tangent. Tangent is opposite over adjacent. So we need to find the adjacent side using the Pythagorean theorem. And we get that the tangent is opposite over adjacent. So the tangent is 3 over the square root of 7, which is the exact same thing that we had before. Now technically when we're finding x here, we did take the square root, so we should have a plus or minus on that side. The plus or minus is going to come into play when we're specifying which quadrant we're in on these problems. In some quadrants, tangent's positive. In other quadrants, tangent is negative. For the test or for the homework, you can do this problem in either way. You can either do it using the identities, or you can do it by drawing the triangle. It's up to you. Next set of things to do in this section: express each value as a trig function of an angle in quadrant 1. And they start us with the sine of 600. For problems like this, we're going to use coterminal angles and reference angles. We actually did things similar to this in Chapter 5. So 600 degrees is more than all the way around the circle. So I'm going to start with 600 and subtract 360 from it. So the sine of 600 is the same as the sine of 240, because those angles are coterminal. 240 isn't in the first quadrant though. 240 is more than 90, it's more than 180, but it's not quite to 270 yet, so it's somewhere in the third quadrant. And the reference angle would be this angle that goes back up to the x-axis. If I take 240 and minus 180, I get that the reference angle is 60 degrees. So the tangent of 240 is the exact same as the tangent of 60. The only thing that might be different is it might be different by a positive or negative. The way we can tell is in the first quadrant, sine would have been positive. In the third quadrant, though, we should have been negative. So it's not exactly the same as the sine of 60. It's equal to the negative version of the sine of 60. And now we've rewritten the sine of 600 as a trig function of an angle in quadrant 1. And that's all we have to do. We don't even need to figure out what the sine of 60 is. We just have to rewrite it as negative sine of 60. We have 3 more examples like that to take a look at. Next one is in radians. The sine of 19 pi over 4. If you are very concerned by radians and you want to change this into degrees, that's fine. But working in radians is going to be the same as working in degrees. 19 pi over 4 is more than 1 trip around the circle. 1 trip around a circle in radians is 2 pi. And since we're in fourths here, 2 pi is the same as 8 fourths, 8 pi over 4. So I'm going to take that 19 fourths and I'm going to subtract 8 fourths. I'm going to subtract 1 trip around the circle. That's just like subtracting 360 was in the last example. And I get 11 pi over 4, which is still more than 1 trip around the circle. 1 trip around the circle is 2 pi. So I'm going to take that 11 fourths and subtract a full rotation again. And I finally get something that is less than 1 trip around the circle. I get that the sine of 19 pi over 4 is the same as the sine of 3 pi over 4. Those angles are coterminal. They end in the exact same spot. But we are supposed to be in the first quadrant. And 3/4, see, here's 0, there's pi, and this is 3/4 of the way there. So 1/4, 2/4, 3/4. Not the first quadrant. So I need to find the reference angle. What fraction of pi is that reference angle? 1/4, 2/4, 3/4. So this is another fourth. The reference angle is pi over 4. So the sine of 3 pi over 4 is the exact same as the sine of pi over 4. It only might be different by a positive or negative. First quadrant angles are always positive. In the second quadrant, sine would still be positive. So just keep a positive sign or put nothing out front. And that's your answer. You rewrote the question as a trig function for an angle in quadrant 1. Two more quick examples that are exactly like that. Cosine of negative 410, and then the tangent of 37 pi over 6. Pause the video and see if you can figure those two out on your own. Hopefully at this point everybody's had a chance to try C and D on your own. Again, pause the video if you haven't, because here are the answers. For C, since I'm at negative 410, I want to add 360 to get a coterminal angle, and I get negative 50, which isn't in the first quadrant, but it does give me the reference angle. The reference angle is going to be 50 degrees. Since cosine is still positive in that quadrant, our answer in terms of a first quadrant angle is the cosine of 50. Now you also could have taken negative 50 and added another 360 and said, okay, it's the same as 310 degrees. And you're back to the same spot. 310 degrees has a reference angle of 50. Cosine's positive in the fourth quadrant, so it's the same as the positive cosine of 50. For the second one, instead of subtracting 360 degrees, we're subtracting 2 pi, or 12 pi over 6. And when you do that 3 times, you finally end up at pi over 6. And pi over 6 is already in the first quadrant. I don't even need to find a reference angle for it. The tangent of 37 pi over 6 is the same as the tangent of pi over 6. Now let's take a longer break. And, oh, this, by the way, is an identity. It's not super useful. You will not be tested on it, but it is true. This identity has to do with all of the reference angle stuff we were just doing, so we don't need to know the identity to be able to do it. Let's take a longer break and take 15 minutes to work on the first part of your homework. This isn't all of your homework tonight. There are a few more problems to do, but pause the video and work on that assignment for about 15 minutes. The last part of the notes today has to do with verifying that things really are true. So here's an example. Simplify the sine of x plus the sine of x times the cotangent squared of x. Some strategies for doing problems like this are to change everything into sines and cosines. And another strategy that works is factoring. And factoring is actually what we're going to do on this one. Because I noticed that both terms have a sine of x in them. So I'm going to factor the sine of x out. If I factor the sine of x out, I get 1 plus the cotangent squared of x. Which doesn't seem to help unless you remember that 1 plus the cotangent squared of x is a Pythagorean identity. And 1 plus the cotangent squared of x, according to our Pythagorean identity notes, equals 1 plus cotangent squared of x equals cosecant squared of x. So I can go to this and replace that with cosecant squared of x. Now let's change everything in terms of sines and cosines. Sine is already in terms of sines and cosines. But the cosecant squared could be changed to 1 over sine squared of x. And the sign that's on the top of the equation can cancel out with one of the two signs. It's sine squared, so there are really two signs down here. And I can cancel one of those out. So that reduces to 1 over the sine of x. And 1 over the sine of x is actually cosecant of x. That takes care of section 7.1. Your homework is a book assignment, and you started some of those problems a few minutes ago. And in addition to the book assignment, there is also a worksheet for section 7.1. What I'd like you to do now is work on the next 3 problems from that book assignment. Work on 14, 15, and 16. And pause the video, and then I will work out the answers so that you can watch and listen to the answers to those 3 to make sure that you're on the right track for the first part of your assignment. So pause the video, and then we'll go through 14, 15, and 16 together. As I go through these, I'm not doing it the only way that works, but I'm doing it a way that works. An A way that's going to work for number 14 is to change everything into sines and cosines. So cosecant is 1 over sine. Cotangent is cosine over sine. Then we have a fraction and a fraction, so I'm going to multiply the top and the bottom by the reciprocal. And pretty much everything cancels out except for 1 over cosine, which is the same as secant. Changing everything to sines and cosines is a good strategy for number 15 also. If you do that, you get cosine times 1 over sine times sine over cosine. And if you cross cancel, everything cancels out. We have the exact same thing on the top as we do on the bottom. On the bottom we have sine times cosine, and on the top we have sine times cosine. When you're multiplying fractions, if everything cancels out, it doesn't equal 0, it equals 1. If it's the same thing on the top and on the bottom of the fraction, that equals 1. For this last one, new strategy that's going to help. Let's start by changing things into sines and cosines. Cosine, cosine over sine, plus sine. And nothing cancels out because this is addition. So you can't cancel the two signs because we're not multiplying, we're adding. And when you're adding fractions, what you actually need is a common denominator. So right now I have cosine squared over sine plus sine, and to make it look like a fraction, sine over 1. If I'm going to add those fractions together, I need a common denominator. So I need to multiply this one by sine over sine so that the denominators are the same. Then I get cosine squared over sine equals sine squared over sine. Since they do have a common denominator, I can add together the numerators. Cosine squared plus sine squared over sine. Remember, when you add fractions together, you don't do anything to the denominator, you leave it alone. Cosine squared plus sine squared, that equals 1. It's a Pythagorean identity. So we've got 1 over sine x, or cosecant x. Use the rest of class time today to continue the book assignment and to continue the worksheet from section 7.1, and we'll go over questions about those things tomorrow in class.